Welcome back to the session. So previously we were discussing about the rectifier circuits and we discussed about the half wave as well as the full wave rectifier circuits. So we have seen in case of a biphase rectifier circuit, we have seen that we are going to make use of two secondary windings and two diodes, and we are going to control both the positive as well as the negative half cycles, and this makes it more efficient when compared with the half wave rectifier circuits. So now an alternative method to the biphase rectifier circuits are the bridge rectifier circuits. So the next topic that we are going to discuss is about the bridge rectifiers. So in case of a bridge rectifier circuits, it will be consisting of 4 diodes, in which 2 diodes with opposite sides will be conducting for the alternate cycles. Like we are going to have 2 diodes that are being placed in such a manner that the 2 diodes will be conducting together in one cycle, and the other arm of the bridge that consists of the remaining 2 diodes will be conducting in the next half cycle. So this is how the bridge configuration we are going to make use by making use of 4 different diodes. So let us name them diode 1, diode 2, diode 3 and diode 4. So by making use of a bridge configuration, by making use of 4 diodes, let us see how the principle of operation lies in the bridge rectifier circuits. And as we know, for the input we are going to make use of the 220 volt or a 240 volt supply lines that is connected to the primary side of the transformer. So this is the AC supply that we are going to receive, and this AC supply that is at the primary side, in case of the bridge rectifiers we were using 2 secondary windings, isn't it? So in order to overcome that, we are going to make use of a single secondary winding, and this secondary winding is going to be acting as a step down transformer where the number of turns compared with the primary are less. So what happens when the number of turns in the secondary are less? So that is going to result in a step down action. This 240 volt that we are going to receive here will be reduced depending on the number of turns to around 20 volt or 50 volt, depending on the ratio of the primary as well as the secondary windings. So here in the secondary side, what we are going to get? We are going to take one secondary winding, and this secondary winding will give us the reduced voltage when compared with the primary winding. So here we are going to receive approximately 20 ohms, and this is connected to the supply. Positive and negative supply. Once we have the supply, we have the diodes that are going to act as switch at various points, and to this we have to connect a load resistance. Only then our circuit will be complete. So we have to choose the load resistance. The first 2 points of the bridges have been connected to the supply. So the remaining terms must be connected to the load resistance. Let us name the load resistance as RL. So here, from here we are going to connect another value. So all the 4 sides of the bridge, the arms of the bridge have been completed. Now the circuit is complete. So this circuit represents the bridge rectifier type of circuit. So in case of the bridge rectifier circuits, we are going to have 4 diodes in a bridge configuration, where 2 diodes alternately are going to conduct at alternate positive and negative cycles. So this is the major circuit diagram for a bridge rectifier circuit. Now we have to understand the operation. How does this bridge rectifier circuit work? So now let us see. We are going to consider during the positive half cycle what happens, and during the negative half cycle what is going to happen. So first let us consider the case during the positive half cycle. During positive half cycle. So during the positive half cycle what happens? let us say this point and this point. Now this point will be positive with respect to this. Let us call it as A and B point. So here A point is positive with respect to the B point. So let us draw from the secondary side of the circuit. So what happens is, from the A point we have the positive. A point is being positive with respect to the B point. So B will be negative and A will be positive during the positive half cycle. Now when you come here at the point, at this point, so here we are going to encounter the voltage that is a positive voltage, and here we are going to encounter a negative voltage, isn't it? So during the positive, we already have discussed about the diode when it goes to the forward bias state and when it is going to go to this reverse bias state. Also we know that when it is forward bias, it is going to go to its on state, and when it is reverse bias, it is going to come to its off state. So this diode as a switch we have already discussed. So keeping the same concept again, that is, the diode is going to turn on and turn off and act like a switch. We are going to consider this point where a positive potential is applied across the anode of the diode. So positive anode. Come back here, positive and cathode. So diode D4, what is going to happen during positive half cycle? Diode D4 is going to be cut off. It is going to go to its off state. Whereas the diode D1 is going to conduct, and let us draw the diode D1, that is going to be forward biased. And coming to this point where we have connected the load resistance. Fine. Now come to the same point here at point B. A is positive with respect to B. So A is going to have a positive polarity, whereas B is going to have a negative polarity connected at this point of the bridge. So at this point of the bridge means what is going to happen here? At the negative potential, cathode is connected, negative potential, whereas D3 is having anode and a negative potential. Now what will happen in this case? Diode D3 is going to be cut off from the bridge, that is, it is going to be acting as an open circuit as the diode is going to be in its off state, whereas diode D2 cathode is connected to the negative terminal, hence the diode D2 will conduct. So from the point B, we are going to have the conduction of, so we are going to have the diode D2 that is going to be in its negative half cycle, that is, the negative cathode is going to be connected to the negative side of the secondary winding. So now D2, this is D2. Now see, come back to the main figure here. D2 is connected to the other point of the bridge, is connected to the resistance RL. So from this point D2, we are going to get the complete the circuit. This is our load resistance, this is our diode D2. Now how will the path for the current flow be established? So the current path flow, positive potential, then the diode D1 is going to act as an on state of the switch. So if the diode is set to be on state, the circuit is going to show it is going to act as a switch, means it will show that the diode will be in its on state. On state is always represented by a short circuit. Okay, so now the current flows here and flows through the load resistance. See here, output voltage is available now at the point RL. So now coming back here, the direction of the current flow started from here, passing through the load, then coming back to the diode, then moving back to the resistance. So this is the path for the flow of current. See, diode D1, resistor, then come back here, go to the diode that is already in its conducting state, and then come back to the secondary winding. So this is the closed path that is offered to the flow of current during the positive half cycle. So during the positive half cycle, which are the two diodes that are going to be on? D1 and D2. So these two diodes are responsible for the conduction or for the output across the load resistance. Similarly, let us consider the next case during the negative half cycle. So during the negative half cycle, what is going to happen? During the negative half cycle, the diodes have to switch off because we are going to have the polarity change across the points A to B. So A and B point, A will be acting negative during the negative half cycle and B will be positive with respect to A. So now coming back to the same point here. Now instead of positive, what is happening? We are going to have a negative polarity. Similarly here, instead of negative, we are going to have a positive polarity during a negative half cycle. So now here we have a negative polarity. Come back again. So here we have negative, diode D1 has an anode. So negative and anode, diode D1 will be in its off state. Similarly here positive and D2. Previously D1 and D2 were on, but now what happens during the cycle is going to reverse from positive to negative. The supply, when it is going to reverse from positive to negative, this positive potential here available at this point of the bridge and the diode D2 having its cathode. So diode D2 will be in its off state. Off state is represented by a open circuit. Whenever we have an open circuit, we know that there will not be any path for the flow of current. So diode D1 and D2, which was previously conducting, now it will be turned off. Followed. So now it will be turned off, and then what is going to happen now? Come back again to the bridge configuration here. So here we have negative and the negative potential and the cathode. Cathode of which diode? Diode D4. So this path is going to be in its conducting state. So we are going to take from the bridge point here, that is diode D4 is going to conduct. Yes, similarly from the positive point, if we are going to encounter from the positive point here, diode D3 is going to be in its conducting state. So diode D3 is in this direction. So diode D3. So this is D4 diode and this is D3 diode. So this diode D3 is connected to the resistor, that is the load resistor. So we are going to draw the load resistance RL, and then it is coming back to which point? To the point here. So it is going to come back to the point here. Followed. So now what is happening? During the negative half cycle, diodes D3 and D4, opposite diodes are in conduction in alternate cycles. This is one cycle, this is the other cycle. Next, when the cycle keeps on repeating, again D1 and D2 will switch on and D3 and D4 will come back again to a off state. Negative cycle, D1, D2 will be in its off state, D3, D4 will be in its conducting state. So now, how is the path for the flow of current now? The positive potential is here. So we are going with the flow of current. Current is flowing, see, it is flowing from this point to this point again. So the output voltage remains in the same direction because the flow of current is on the same direction across the load resistance. So this will follow the path here. Come back here, then come back here, go back to the secondary winding. So this is the path for the flow of current. From here, this is the starting point, it flows like this across the load resistance and comes back to the diode D4, back to the secondary winding. So this is the path for the flow of current. This is how a bridge rectifier makes use of the 4 different diodes and gives us a full wave rectified output. So now let us see the waveform, how we are going to get. So initially we have the sinusoidal. This is our input, sinusoidal input. So the sinusoidal input, we have a positive cycle, negative cycle, positive cycle, negative cycle. This goes on with respect to omega t. So let us call V in as the input with some peak value plus Vm and minus Vm and 0. Okay. So successively 0, pi, 2 pi, 3 pi, 4 pi, 5 pi and so on. So this is our input voltage. Now whatever we have discussed till now, the same thing we are going to put it in the form of a waveform. Okay. So now what is happening during the positive half cycle? We are going to get an output across the load resistance. So that is in the same direction. So the output that we are going to get with respect to the input, first you have to draw the line in such a way that for each cycle we have to show the respective waveforms and the conduction of the respective diodes. Now how we are going to get the output voltage and how we are going to plot it? So output voltage that we are going to get is because of the presence of diode D1 and D2, and we are going to get a flow of current in this direction from positive to negative, that we are going to consider as the output voltage. So almost the same shape Vm will be retained. Okay. Now coming to the negative half cycle. The negative half cycle is this portion. So during the negative half cycle, what is happening? Diode D3 and D4 are going to conduct, and because of the diode D3 and D4 in conduction, see the direction of current? Direction of current is from positive to negative only. So the output voltage will not change its direction. It will be in the same positive axis. It will be in the same positive axis. Okay, so the current is flowing back to the supply. So this cycle keeps on repeating. Positive half cycle, because of the responsibility of diode D1 and D2, we are getting this. Next, because of diode D3 and D4, we are going to get the next part. Then again positive half cycle, D1 and D2. Right? So this is how we are going to get the full wave rectified output. Full wave rectified output that we are going to get is because of D1 and D2 in the positive half cycle. Let us say this is 0 to pi, pi to 2 pi, 2 pi to 3 pi, 3 pi to 4 pi, 4 pi to 5 pi. This is the time period. So positive half cycle, responsibility of D1 and D2, because of these diodes we are going to get. Next, in the negative half cycle, it is because of D3 and D4 that we are going to get. Again repeats, D1, D2 is responsible during the positive half cycle, D3 and D4, again D1 and D2. This continues as the cycle keeps repeating. So hope you have understood the working principle of a bridge rectifier circuit. We know that we want to get a output as a DC. So we want to smoothen the waveform. In order to smoothen the waveform, we have to make use of, as the previous circuits we have used, we have to make use of the reservoir or the capacitive circuits, or we call it as a smoothing circuit, in order to remove the ripple content. So you can observe one more thing here compared to your half wave rectifiers. Here the output voltage that we are going to get is twice the input voltage compared to your half wave. In half wave what happened? Only one cycle, either positive or negative was conducting. So either positive or negative we used to get only one cycle. One value, that is Vm, we used to get for the output voltage. But in case of a full wave rectifier, like in case of a bridge rectifier, we are going to get 2 Vm. For one cycle we are going to get twice the input voltage. So that is the advantage, and hence the efficiency of these type of circuits are also more, around 80% when compared to the efficiency of the half wave rectifier. So in order to smoothen the waveform, we have to use suitable smoothing circuits, and we know that we are going to use the capacitor for the smoothing action. So bridge rectifiers with reservoir circuits. The next topic that we are going to discuss is with reservoir circuit or smoothing circuit. So operation of these diodes remains the same. What is the functioning of this capacitor is, when the diodes are going to be in its off state, diode D1 and D2 is conducting now, next cycle when it is switching over, then what happens? This diode is going to be in its off state. So before that state, the capacitor starts storing the charges during the positive half cycle. Then what happens? Again the negative half cycle is going to take place, and D3 and D4, so it achieves or it provides a path for the continuity of the waveform, and hence when we are going to keep a capacitor in between the load output voltage as well as the bridge circuit, we are going to get a smoothened waveform. So how that smoothened waveform is going to represent? So this is our waveform that we have got at various Vm values at the same. This is the waveform what we have got, and the capacitor will start charging as the output voltage is going to be obtained during the positive half cycle. Next, when the diode is going to discharge, when the diode is going to go to its off state, it gradually discharges till where? Till the next cycle, again charges, again it discharges, again it charges to the maximum V peak, again it discharges, again charge and discharge, charge, discharge. So the ripple content has been reduced here, and this is how we are going to get the ripple content, and hence the output voltage when we are going to make use of a capacitor. So this is the effect of adding a capacitor. Instead of getting a large ripple, we are trying to reduce the ripple content in order to get the circuit in order to make the circuit more efficient. So we will be using a capacitor as a smoothing or a reservoir element. As we have discussed the main block, that is the power supply block diagram, we came across the different parameters like the step down transformer, then we discussed about the rectifiers, then to the rectifiers we studied about the intervention of the reservoir or the smoothing filters in order to make the wave smoother. So similarly, after the point where we are going to attach a smoothing filter, we also have a provision to regulate the level of voltage. Why this voltage regulator? Now for our specific application, we require the certain level of voltage. Now if we are going to say, as we took the example of charging of the battery of our mobile phones, so what is that? For some mobile phones we require only 18 volts of voltage to be charged to the battery. So above that it can damage the other components that are present in the device. So what we are going to do is, we always have the regulator, voltage has to be regulated, and we already know that the voltage regulation will take place with the help of a Zener diode. Okay. So let us study about the voltage regulators. So what do you mean by regulators? Voltage regulators will help us regulate the voltage to the desired level of voltage. So whenever we have this voltage regulator circuit, at the input that we are going to feed to the regulator will always be an unregulated input. So which is not regulated. Now we have studied about the bridge rectifier the previous sessions. The bridge rectifier, the output that we got from a bridge rectifier, after passing it through a smoothing filter, we got with some ripple content with it, isn't it? That is known as the unregulated input. So we know by default we have to make use of a Zener diode, which is which operates or which regulates the level of voltage. So Zener diode has to be used, which is going to help us to perform this regulation operation. But before sending it to the Zener diode, we know that the Zener diode requires only around 2 milli to 5 milliamperes of current. So whatever the voltage, let us say we have the output voltage previously to the bridge rectifier circuit, we have 20 volts of voltage available with us. We have to reduce it to 18 voltage. So now in order to do that regulation, we have to use a suitable resistor which is going to limit the value of current. Okay. So now in order to limit the value of the current, we have to use a resistor in series. So this resistor that we are going to use in series to limit the current that is flowing through the Zener diode. Now once we have the Zener diode, we cannot leave it as it is because our end destination is the load. So we already have the presence of a load element. So a load resistance is present, and this RS is the resistor that we are going to choose in order to limit the flow of current. So this Zener diode, what happens when the current is flowing? Maximum part of the current is flowing through the load resistance, and there will be a minimum current flowing through the Zener diode. Through which the Zener diode is going to perform its operation. So the output voltage that is available will be present at the Zener diode itself. The VZ voltage, the the output voltage that we have to pass it here will be present here itself, and this will be depending, this will make the voltage that is present here, that is going to be supplied across the load, will be determined by the potential divider circuit. So now at this point you can see it acts as a potential divider. So the ratio of this RL and RS plays an important role in defining or in determining the level of voltage that we are going to pass at the load resistance, that is the actual output voltage. So in order to find out, how do we find out the value of Vz? So the value of Zener diode, how can we calculate, is nothing but the unregulated input that we are going to give Vin into the voltage divider circuit. So apply the potential divider or the voltage divider circuit, Rs plus RL. So this is how we determine the voltage Vz, and this ratio plays an important role in such a way that the value that we are going to select for the RS, so for limiting the current, plays a vital role in finding out what is the type of regulation or what is the amount of regulation that we need across the output voltage. So in order to find out the value of RS, so current limiting resistor means we should have a maximum and minimum values for a resistor in such a way that we have to choose a optimum resistance value. So in order to get the maximum value of the resistance, yes, RS maximum, okay, we have to choose the resistance in such a way that depending on, already we have the output resistance or the load resistance to the ratio of Vin divided by Vz minus 1. We have the equation to find out the maximum value that we can choose for a regulator, that is given by Vin by Vz minus 1. So this determines what should be the value of the current limiting resistance maximum value. So we know that whenever we have a Zener diode, the power dissipation across the Zener diode. So we know that whenever we have a Zener diode, the power dissipation is given as V into I. So power across Zener diode is equal to Vz into Iz. So now we will calculate what is the value of Rs minimum. So Rs minimum is given as Vin minus Vz divided by Iz. Okay, so Vin minus Vz to the current, Zener current that is flowing. So instead of Iz, can we use this equation for power and write Pz divided by Vz. Now we are finding out the minimum value. So we have the current here in the denominator. So what should happen? The maximum power should be there in order to get, maximum power dissipation should be present in order to get a minimum resistance. So Vin minus Vz divided by, instead of Iz we are going to substitute Pz, maximum power dissipation, divided by Vz. Bring this Vz to the numerator. We will be getting it as Vin into Vz minus Vz square divided by Pz maximum, which gives the value of the minimum resistance. So this is the equation that we choose for the maximum resistance, and this is for the minimum resistance. So in order to perform the regulation, we need to concentrate on the values of Rs and RL to get a specified regulated output voltage. Now in concern with this, if we want to find out what is the output resistance as well as what is the regulation that is to be carried out in a perfect power supply, the output voltage will never change for any change in its input, isn't it? But practically what happens is, whenever there is a change or variation in the load current, so if the load current is increasing, then automatically the output voltage keeps decreasing. This is what happens in practical. So we say that the power supply has some internal resistance, isn't it? So that internal resistance is represented in the form of the output resistance. So what is this output resistance? Usually by Ohm's law, how do we define resistance? The output resistance. Whenever we say Ohm's law, we say whenever we have the resistance, we find it out by V by I. Voltage by current gives us a resistance. So in case of the output resistance, for a small change in the voltage, output voltage will result in a small change in output current, and this ratio of change in output voltage, I will write it here, the change in output voltage to the ratio of the change in output current, is defined as the output resistance for a power supply. Similarly, we have another term known as the regulation. So for a power supply, we need to find out the regulation. What do you mean by this regulation? Now for some input that we have given, we are going to get some output. Okay, so if you are going to change the input, even the output also will change. So this regulation must be very small. And how do we define this regulation? Regulation is defined as the ratio of the change in output voltage to the change in input voltage, and always this regulation is expressed in the form of percentage. So we have to take change in output voltage to the change in input voltage multiplied by 100, because regulation is always expressed in the form of its percentage. So this is the output resistance and regulation of a power supply. We have already discussed about the half wave rectifiers, isn't it? So now now for a half wave rectifier, if we are going to now for a half wave rectifier, if we need to improve the level of voltage to the same circuit, then how can we do it? How can we increase the level of voltage to a simple half wave rectifier that we have already come across is by making use of an extra diode and a capacitor. So how to implement or how to incorporate this extra diode and a capacitor is going to be discussed under the heading voltage multipliers. So voltage multipliers means what? We need to get a higher level of voltage than the expected. So that is known as multipliers. So for a voltage multiplier, let us consider a simple half wave rectifier circuit that we have already come across. So that is connected to an AC supply. This is the primary winding of a transformer, and from this primary winding we are going to connect it to the secondary winding with less number of turns to the transformer. And half wave rectifier, as already discussed, we are going to come across only one single diode, and let us say we are going to use a capacitor. Okay. So let us call this as diode D1 and capacitor C1. Okay. Now we are going to use a resistor, a load resistance RL. Fine. Now during the positive half cycle, what happens? Diode D1 is going to be turned on because anode of diode D1 will be connected to the positive half cycle, and hence diode D1 will be in conducting state and the current flows through the capacitor, and even the capacitor starts charging. Okay, this is what we have studied for a half wave rectifier. So let us consider another diode that we are going to connect in such a way that we are going to have a capacitor also present along with the diode D2. During the positive half cycle, what happens here? Diode D1 is going to turn on, whereas the diode D2, cathode of the diode D2 is connected. So what will happen to the diode D2? Exactly, it is going to be in its off state. So what happens? Already the capacitor has been charged, and similarly here also the capacitor will start charging. Let us consider another capacitor C2. So it also starts charging. Now what is going to happen? For one single connection itself, Okay, we are going to take the load not only from one capacitor, combining these two capacitors together, let us consider the output across the load resistance. So, C1 plus C2. So, C1 what is happening? Maximum voltage plus Vm will be stored. Here also maximum voltage plus Vm. So, plus Vm you will get 2 Vm. So, the output voltage here that we are going to get will be the twice of the input voltage. That is how you have multiplied the circuit. So, in this connection, during the negative half cycle what happens? During the negative half cycle, diode D1 is going to be in its off state because anode is connected to the negative, whereas diode D2 will be turned on, and this diode D2 will have the path for negative, positive. See the direction, negative, positive, negative, positive. So, again the negative half cycle also we will be getting V0 is equal to 2 Vn only. So, this type of circuit is known as the voltage doubler circuit. Doubler means we are going to get 2 times the output voltage is 2 times the input voltage that we have applied. So, it is known as a voltage doubler circuit. Like this, the efficiency of the circuit increases, and this type of voltage multiplier is suitable only for small currents. Okay. Now, voltage doubler, similarly, if by using an extra capacitor and a diode combination, we can have the voltage tripler circuit also. So, voltage tripler circuit is consisting of 3 capacitors and 3 diodes. So, in case of a voltage tripler circuit, this is how the configuration of a voltage tripler circuit lies, and we have 3 capacitors and 3 diodes arranged in such a way that when we are going to add up the voltage, that the voltage we are going to take will be across this load resistance RL. So, this voltage that we are going to receive at the output voltage, that is the load resistance, will always be 3 times the input voltage. So, this circuit output voltage that we are going to receive is 3 times the Vn, hence it is called as a voltage tripler circuit. Like this, we can make use of the multiples of the voltage as a voltage multiplier, but what happens if the voltage multipliers will keep on reducing, it becomes impaired as increasingly by using the higher order multipliers. So, that is the reason we do not go with the higher level of multipliers. We make use for the voltage multipliers for a very small current. So, this is about the voltage multipliers, the doubler circuit and the tripler circuit. The next part of the session is about the amplifiers. So, as soon as we see or hear the term amplifiers, what comes into our mind, what pops up in our mind? Now, let us say I am in a closed room, I am speaking in a closed room, and with this volume of my speech, I hope it is audible for all the students or all of you all present inside a room. Now, with the same voice or with the same tone, if I am going in an open air or a ground and I am going to address more number of people with the same voice, is it possible for all of them to be audible to whatever I am speaking? Definitely it cannot be possible. There is that, at that point, this amplifier pops in. So, what is this amplifiers? So, you know there is an audio amplifier, there is a mic set, there is an audio amplifier, and to whatever I speak, depending on the audience and depending on the surrounding that is going to be present there, I am going to tune the amplifier, isn't it? So, what I am going to do, if there are more number of people surrounded in that area and they cannot hear what I am going to speak, I have to increase my volume of the tuned amplifiers or the audio amplifiers, isn't it? So, what happens? There comes into picture of what is this amplifier. So, while speaking, we have come across this audio amplifiers very often, like the mic sets that we are going to use. It is not audible, increase the volume. It is going to be hazardous to the ears, we are going to reduce the volume, isn't it? So, let us now discuss about what is an amplifier. So, amplifier means it is an electronic circuit that makes use of an external power supply and gives an output always larger than the received input. So that is the speciality of this amplifier circuits. So that is the meaning of an amplifier. It is a circuit that receives the external power supply and gives the output always higher than the received input power supply. Amplify. So as the word itself indicates that amplify means increase. What we are going to increase? We are going to increase the different parameters in electronics, that is the voltage, current, power. So if we are going to increase the level of voltage when compared to the receiving input, that is known as a voltage amplifiers. If suppose the current that is flowing inside the circuit, amplifier circuit, is going to be increased, that is known as a current amplifier, and the power that we are going to put it in a circuit and we are going to increase the power of the circuit, we call it as a power amplifiers in general. So the amplifiers, depending on what parameters you are going to amplify, have been classified as current amplifiers, voltage amplifiers and power amplifiers. Apart from that, we have few more types of amplifiers like the AC coupled amplifiers, DC coupled amplifiers. So in an AC coupled amplifiers, we are going to couple the different stages of amplifiers, eliminating the DC component. That is why it is called as a AC coupled amplifier. When coming to the DC coupled amplifiers, the stages are coupled in such a way that we are not able to provide isolation for a DC. So there are no isolation between the stages. Both the AC as well as DC components are coupled from stage to stage. So that is the meaning of AC coupled amplifiers and DC coupled amplifiers. So the next type of amplifiers are based on the level of voltage that we are going to consider. So they are known as large signal amplifiers. Large signal amplifiers means let us say the amplifying level of voltage is around 1 volt to 100 volt. The type of amplifiers which caters the signal strength from 1 volt to 100 volts for its amplification purpose is known as large signal amplifiers, whereas if we are going to have the amplifiers for less than 1 volt, such type of amplifiers are known as small signal amplifiers. So when we are discussing about the different transistor and its characteristic or MOSFET and its characteristics, we go with the small signal amplifiers. So this is the next type of amplifiers. The next type of classification are based on the frequency range. So the next type of amplifiers are audio frequency amplifiers. So audio frequency, what is the audible range of frequency that we can hear? That is from 20 hertz to 20 kilohertz. If the amplifier circuits are going to operate within the range of audible frequency, such type of amplifiers are known as audio frequency amplifiers. Next, similarly, if we are going to encounter the wide band frequency, or this is for the audible frequency we want, that is from 20 hertz to 20 kilohertz, we are going to make use of a circuit and we are going to call such amplifiers as audio frequency amplifiers. Similarly, wide bands means, say for a large band of frequencies, say from few tens of hertz to some megahertz. Few tens of hertz to several megahertz. If this amplifier circuit is designed for such a frequency range, we call such amplifier circuits as wide band amplifiers. Similarly, the next type of amplifiers we have is the radio frequency amplifiers. So radio frequency amplifiers usually operate from 100 hertz to across 1 gigahertz. So this is the radio signal range, frequency range. So if the amplifier circuits are encountering or catering such type of frequency ranges, that type of amplifiers are known as radio frequency amplifiers. So these are some of the types of amplifiers, and along with this we have the noise, and some of them, the another type of amplifier is to cater the low noise, negligible noise. So we call it as low noise amplifier. Approximately less than 10 millivolt signal level, a very small signal level is used, and hence it is known as, that is a very negligible noise will be encountered. So a low noise amplifier is the another type of amplifier. So these are the various types of amplifier that we have come across. Once we have discussed the types of amplifiers, we have few parameters that we have to know. When we speak about communication, then we have to know few terms like what is frequency, what is a bandwidth. So we will discuss all the different basic concepts that we encounter in. So now we have discussed the different types of amplifiers. Let us discuss few parameters that we encounter in an amplifier. So whenever we say a circuit, we know there are some input and there is some output for the given input in case of an amplifier. So what is that we are going to get? Amplifier means what? Always we have to get a higher output when compared to the given input. So that is expressed in the form of gain, which plays a very important role in amplifiers. So what is this gain? Gain is defined as the ratio of output to the ratio of input. So we can define in terms of different parameters. Now if we want to define it as voltage gain means, how will you define? The ratio of output voltage to the ratio of input voltage is defined as voltage gain. And always remember, gain does not have any unit. Okay, so output voltage by input voltage is defined as gain of an amplifier. Voltage gain of an amplifier can also be expressed as A suffix V. Gain is usually expressed as A. So we are speaking with respect to voltage gain. So we represent it as A suffix V. Similarly, if we are going to define the same gain parameter with respect to its current, so we call it as current gain. Gain is represented as A, and for current we give I. So A suffix I is given as output, the ratio of output current to the ratio of input current is defined as the current gain. Even the current gain does not have any unit. Okay. Similarly, power gain. So power gain means, now can you guess what will be this power gain? Power gain is represented as A suffix P. A suffix P means output power, the ratio of output power to the ratio of input power is defined as the power gain. And even power gain AP can also be expressed as, we know voltage into current gives us power. So voltage gain into current gain can also be written as the power gain. So this is one of the important parameter of an amplifier, that is gain of an amplifier. In terms of voltage gain, current gain, power gain, you can express the gain of an amplifier. Parameter that we are going to come across, the parameters in amplifiers, is the input output resistance. So what do you mean by this input output resistance? Input and output resistance. Now for a small change in the input, let us consider this is the input resistance, and let us consider this some value of resistor or some load element we are going to, some input resistance we have and some output resistance we have. So the ratio of the output resistance, that is the voltage that is changing, the input output voltage that is changing for a small change in input output current is known as the input output resistance. So this is also one of the parameter which determines what is the presence or what is the change that is taking place within the input output voltage and current. The next parameter that we are going to encounter is the frequency response. So frequency response means what? The values that we are going to plot, the gain values that we are going to plot across the different values of frequency. Along the x-axis we are going to take the frequency components, and along the y-axis we are going to plot the gain components, and this plot of frequency versus gain is known as the frequency response. So, frequency response of a system or of an amplifier is for different values of frequency we are going to plot the different gain values, and this is usually plotted in the form of the semi-log graph sheets that we are going to use, that not the normal graph sheets. We will be plotting the frequency versus gain. Gain is expressed in decibels. So, this plot is known as the frequency response. It can be from a higher value to a lower value, and then again it keeps on varying depending on the various frequency plots that we are going to use. Now, frequency response means for a change in frequency, what is a change in the gain that we have attained. If it is plotted, then that is known as the frequency response. Now, if the value is, let us say, if you are going to measure the output power, okay, or if you are measuring from the voltage gain part. So, if it is output power, 50% of the output power that we are going to consider. Okay, let us say if this is the power maximum and this is the half of the power maximum. So, this point will be the point that is used to measure the frequency. So, in frequency response we include the parameters such as high cutoff frequency and low cutoff frequency. Cutoff frequency. Okay, in that we have one is high value and the other one is the low cutoff frequency. So, what do you mean by high cutoff frequency and low cutoff frequency? Now, if we are, say for example, this is a frequency plot and this is a maximum power that we have taken for the frequency plot, and this is the half of the maximum power, or if it is a voltage gain that we are going to plot along the y-axis, then 70% of the voltage gain. Usually when we are using or when we are plotting a frequency plot in a semi-log scale, then we are going to show minus 3 dB difference. Below minus 3 dB difference, we are going to take the cutoff frequencies. Okay. So, this is the range at which we are going to take. So, at this point, at the 50%, the rising of the response we are going to take, this gives us the low cutoff frequency, lower value of the frequency, hence it is called low cutoff frequency. As the frequency keeps on increasing, at another point when the falling of the response is taking place here and we have a difference of minus 3 dB difference. So, then this part is known as the high cutoff frequency. Followed low cutoff frequency and high cutoff frequency, and this difference between the low cutoff frequency and high cutoff frequency, this part is known as the bandwidth. So, how do you define bandwidth of an amplifier or bandwidth of any signal? Bandwidth of a signal is defined as the difference between the high cutoff frequency as well as low cutoff frequency, which is termed as bandwidth. Next, we have the next parameter, phase shift. So, what do you mean by phase shift? So, phase shift means the shifting of signals with respect to some angle difference. Now, let us consider the sinusoidal shape of waveform. Yes, this is the first waveform. Now, let us say after some lagging parameter with the second signal is going to start. So, now you can observe there is an angle difference. The amplitude remains the same. What is the change that we are going to find here? Only the angle change. So, this is known as the phase shift. The shifting of the angle of one signal with respect to the other signal is known as the phase shift. Fine. So, these are the different parameters that we are encountering when we are discussing about the amplifier circuits. Next, let us see the concept of feedback. What do you mean by feedback? Now, we know we are in a system. Now, let us say I am feeling very hot. So, when I am feeling hot, as soon as I enter a room, what happens? I tend to turn on the fan. So, when I turn on the fan, then what happens? The speed at which the fan is delivering the air is not sufficient for me. Then what I do? I am going to increase it. There is already an input, you are giving the input by turning on the fan. the fan that is rotating is producing some output. Between this input and output, I am the feedback element. Depending on the output level, what is the output I require, I am going to give a feedback by changing the speed of the fan. So, this feedback in any of the system that we are going to implement. So, this feedback plays a very important role in any system. Okay. Now, I want to increase the speed, I am increasing the efficiency. Now, I am increasing the speed of the regulator. Now, if I am feeling very cold, what I am going to do? Either I am going to turn it off or I am going to reduce the speed of the regulator. So, this feedback that I am going to get is going to give a desirable output. I require some output. So, because of that output, I am going to change the feedback. Okay. So, that is the concept of feedback. So, in case of amplifiers also, we have the concept of feedback, and for this feedback, we are going to make use of two types of feedback. If you are going to feedback a positive value, okay, then it is known as a positive feedback systems. Positive feedback amplifiers, usually it is known as the oscillator circuits. Okay. Next, negative feedback. Either you give a positive feedback or you are feeding back a negative point. So, the negative in the case of the amplifiers, we are going to make use of the concept of negative feedback. So, since we are discussing about the amplifiers, now we have to go further with the explanation with respect to what is a negative feedback. So, the next part is the negative feedback. Amplifier output with negative feedback. Now, let us see, we are going to get an input, an amplifier circuit is given, and in this amplifier circuit they have specified the gain, internal gain of the amplifier to be AV. AV means what? Voltage gain, and a phase shift. I already told you what is a phase shift. Phase shift means shift. The signal is going to shift from one another with an angle of 180 degree. Okay. So, we have got a positive to negative signal. Okay. So, this is the signal that we are going to get. We are going to take the negative to positive. So, that input, let us say the input that we are going to feed here is V in dash. Okay. Why V in dash? Later I will come back when we are speaking with respect to negative feedback. So, this is the forward path of the system. So, here we are feeding an input, an amplifier is there. It is shifting the phase by 180 degree. Now, what do you mean by this shifting the phase by 180 degree? The signal that we are going to apply is from 0 positive, then 0 negative. Now, if you are telling 180 degree phase shift, then what should happen to the signal? The signal totally should reverse like this. If it is positive, it will reach negative. So, this is the meaning of 180 degree phase shift. Did you understand? So, the amplifier that they are specifying is at 180 degree phase shift. So, what happens? The signal that you are going to give, positive, negative, will become negative, positive because of the phase shift 180 degree. Okay. So, this amplifier output that we are going to encounter is the same output that we are going to receive here with an inverted output, because the amplifier has phase shifted the signal by 180 degree. Next, once the amplifier is shifted, now we are speaking with respect to a feedback element. Remember, I told you the switch is the input, the fan is the output, and I am the feedback element who is going to control the speed of the fan depending on my desire. I am desiring to have a high speed or a low speed. Depending on that, I am going to control the regulator. Similarly, now we have a feedback element. The feedback ratio is having some gain of beta, and again it is going to phase shift by 180 degree. So, now the signal that is entering is nothing but minus to plus here. Now, the signal that is entering from here is, see what is that is coming here? The positive is coming here. So, the positive, and this part is the negative. So, positive, negative. So, this is the direction of the feedback that you are going to give. The signal is at plus and minus. Plus, see, plus is from this side, minus is from this end. So, the output is going to be inverted and fed back. So, what you are going to feed here? V out is going to be fed here. So, multiplied by the ratio, the output ratio here, we are going to get it as beta into V out. will give us the V in dash, isn't it? So beta into V out, what is the sign change? So now it is plus, here it is minus, again 180-degree phase shift. So if the signal that is positive, if we say it is encountering a phase shift of 180-degree, it is going to completely invert. So instead of having plus here, we will be having minus here and plus here. So this signal is going to come back to the input, and here applying the Kirchhoff's voltage law, how can we write? Applying the Kirchhoff's voltage law, how can we write this? V in dash is equal to, how do you express V in dash? V in minus beta into V output, because see the sign change, V minus beta into V out, V in, so V in dash is nothing but this V in dash is the actual input to the amplifier. Okay, considering the feedback element, we are going to get the actual input as V in dash. Now this V in dash, call this as, we can rewrite this in terms of V in as, bring this V in out, V in dash, bring this beta into V naught to the other side, it will become plus beta into V out. Call this as equation number 1. Similarly, the internal gain of the amplifier. Okay, before defining the KVL, now this is a general amplifier circuit. So for a general amplifier circuit, how do you define the gain of the amplifier, of the total amplifier? The output voltage divided by the input voltage is given as the gain of the entire amplifier, isn't it? So let us call this as equation 1, and this let us call it as equation number 2. Got it? Next, what you are going to do? We are considering the internal gain of the amplifier. So for the internal gain of the amplifier, V out is the output voltage, V in dash is the input voltage. So considering the internal gain of the amplifier, AV is equal to, what is that AV? V out divided by V in dash. Now if we want to express in terms of V out, can we write it as AV into V in dash? Yes, we can write it as AV into V in dash. Okay. So now call this as equation number 3. Now what are you defining? We are defining the gain. So substitute equation 2 and 3 in equation 1. We are going to get the gain G. Gain is represented as capital G. V out is given as AV into V in dash whole divided by, what is V in? V in is expressed as V in dash plus beta into V out. But V out is again AV into V in dash. So now substituting back in terms, instead of beta into V out, substitute equation 3 value. So we are going to get it as G is equal to AV into V in dash whole divided by V in dash plus beta, instead of V out, let us substitute AV into V in dash. So AV into V in dash. So now take out V in as common. So AV into V in dash whole divided by V in dash is taken as common. So V in dash 1 plus beta into AV. So V in dash and V in dash will get cancelled. Therefore, the gain of the system G is equal to AV divided by 1 plus beta AB. So by making use of a negative feedback, we can achieve, or we can overall control the gain of a feedback, gain of an amplifier. So this is the main reason why we are going to choose a negative feedback for an amplifier, in order to control the gain and increase the bandwidth and reduce the distortion. So this is the negative feedback of an amplifier. Thank you.